So let me start by introducing our speaker today, Aleksi Kurkela. He got his PhD in theoretical physics from the University of Helsinki in 2008. He had two postdoctoral positions, one at ETH Zurich in between 2008 and 2010. From 2010 to 2013, he was a postdoc at McGill University. He then was a CERN Marie Curie Fellow from 2013 to 2015. And studying from 2015, he became an associate professor at the University of Stavanger and a staff member at CERN Theory. In 2019, he received the Zimone Nuclear Theory Award at the Quark Matter Conference in Wuhan. And he worked on this field. Actually, he worked in many different topics over the years. This recent work in nature physics attracted a lot of attention, and basically that's the topic of his today's talk. So with that, I'll give the microphone to Aleksi.
Okay, thank you very much for the kind introduction. So this talk is going to be about strongly interacting compressed matter in the course of neutron stars. I have here, this talk is mainly based on these references that I have here on the slide here, mainly there to show my collaborators' names there who have worked a lot in this project. Now, in general, matter in extreme conditions reveals its constituents. And this happens to nuclear matter made out of protons and neutrons when you heat the matter up to very high temperatures, or you compress to very high densities, where the matter becomes elementary particle matter made out of quarks and gluons, the fundamental constituents of nuclear matter. Now, from the empirical, experimental, observational point of view, we live in a beginning of a new era of studying strongly interacting matter in extreme conditions. On one hand, we have the precision frontier in colliders with LHC, scheduled runs 3 and 4, and the high luminosity upgrade of it, and other new collider experiments like FAIR and NICA that will characterize and study the hot quark gluon plasma, the hot quark matter, in unprecedented detail in the next few decades to come. And at the same time, we have the new discovery frontier in study of strongly interacting matter in the course of neutron stars, which has been made possible by the rapid advancements, the advent of gravitational wave and multi-messenger astronomy, together with the rapid progress in more traditional radio and X-ray astronomy. And so this talk will be about the neutron star aspect, the discovery frontier, but I will make some remarks coming from heavy ion background of my own with the connections to heavy ion physics. Okay, so I'm sure everybody here knows what neutron stars are, but just to get us all on the same page, neutron stars are endpoints of stellar evolution. They have masses up to roughly 2 solar masses, and they are extremely dense. Their radii are of the order of 10 kilometers. They are hot objects, astronomically speaking, but from the nuclear physics point of view, after a short period after their birth from a supernova explosion, they cool down to temperatures which are at least small in nuclear physics terms in this talk. Now, we cannot look directly to the core of a neutron star, so we do not know what is the density at the core of a neutron star. But models show that the densities in neutron stars may reach densities that are as high as 10, 15 times the nuclear saturation density. That's the density, roughly 0.16 over Fermi cubed, what you have in very large atomic nuclei. Now here on the right hand side, I have a. Do you, by the way, see the pointer if I put my mouse?
Yes.
So here is a cartoon of what a structure of a neutron star might look like. It's certainly not in scale. And if you could open it up like a pizza slice. And here I just want you to concentrate on the large question mark at the core. We do not know what the matter is in the core of a neutron star. And so what I try to address in this talk is how can we understand these objects from first principles. Now, what sets the numbers in that previous slide is a competition of two forces. On first, the gravity tries to pull the neutron star into a black hole, and at the same time the pressure of strong interactions pushes that back. And that competition sets the scales there. In the most simplified, simple-minded approximation of non-rotating spherically symmetric case, this competition is codified by the famous TOB equations, which are the Einstein equations in spherically symmetric system in presence of matter. And so in order to complete these TOB equations, you need to tell how does the matter behave, and that is described by the equation of state. And so the equation of state then codifies the properties of strong interactions. And that will be a central object in this talk. Now, this competition makes these neutron stars mappings of microphysics to macroscopic physics. So whatever the macroscopic features of the star are, they reflect the microscopic features of the matter because of this competition. And that makes them especially useful. One way to see this competition is, for example, in this iconic mass radius sequences. So if you give me an equation of state that you got from somewhere, we can run it through the TOB with different central pressures, and we can find out what is the relation between the mass and the radius in different stars. And this is unique for a given equation of state, and it reflects the material properties of the stuff that the star is made out of. For example, if you would have a very small star, very light star, it would have a large radius, for example, here. And now if you keep adding matter to this star, so you increase its mass, the pull of gravity will increase. And because at this point, the central densities are below the nuclear saturation density, the matter is fluffy. So you add more stuff, you add more gravitational pull, the radius of the star will at the end decrease. And this will continue until you reach roughly at the center of the star, you reach the saturation densities, which is the point when the strong interactions really start pushing back. And at that point, you see a change in behavior. The matter becomes more stiff, and the radius doesn't anymore, for this particular equation of state, does not reduce anymore. Eventually, if you keep adding matter to the star, you reach a point where the nonlinearities of the gravity win. They always win at some point, and that is the maximal mass of this equation of state. And each and every equation of state have a maximal mass, which depends on the microscopic details of the equation of state. So in this way, the macroscopic properties, in this case the mass radius sequence, depend on the microscopic details of the equation of state. Now, so this makes these neutron stars into fantastic microscopes, or I should say femtoscopes, that that map the physics from the scale of the size of a neutron, 10 to minus 15 meters, to the scale of neutron stars in 10-kilometer range. So they are femtoscopes with a magnification ratio of 10 to 19. And this is, of course, a fantastic property of these neutron stars, but from the observational point of view, it is slightly difficult because the closest neutron stars are 10 to 19 meters away. So that's the challenge. We should not forget our other femtoscope that I mentioned earlier. We have a long history of experimentation with nuclear beams. And if I would have to put in the experience of that into one sentence, that would be that we know that matter hot quark matter or hot matter undergoes a transition to quark matter at some energy density, which is roughly 500 MeV over Fermi cubed. At that point, the matter goes into quark matter phase. And now these energy densities are not outlandishly high compared to that what you expect to find in a neutron star. And so that raises the question, the big question that I would like to understand, that is there an analogous cold version of this quark matter appearing in the cores of neutron stars? And that is the big question that I would like to understand, and that I will try to address at the end of this talk. So the outline of this talk is that I'll first have a very brief outline of those relevant neutron star observations that give us the most direct information about the material properties of the neutron star. And then I will discuss what we know from theory, from if you wish, terrestrial experiments about the equation of state. What do we know about that? And then I will bring these two sections together by asking how can we use astrophysical constraints to improve our understanding of the equation of state in the regime where we cannot do direct first principles calculations. And finally, I will try to address the big question: is there quark matter in neutron stars? So we have many measurements of neutron star masses. And, here is a famous list of most known neutron star masses. They come in binaries because you need to have the orbital mechanics to extract the masses of these. There are many different types of systems here. The most important for this talk are these two stars here. I'll call them the Demoresque and star, whose mass has been measured with a very robust and an accurate Shapiro delay method, which basically is a pulsar timing method where you keep track of how the signal gets delayed, goes through the gravitational field of the companion star, in this case, in these cases, a white dwarf. And there are two very accurate determinations of two very massive stars, roughly 2 solar mass stars. And their mere existence is extremely interesting because, as I mentioned, each and every equation of state has a maximal mass. And any equation of state that cannot support these 2 solar mass neutron stars cannot be the correct equation of state that is reflected in the nature, just by the mere fact that if nature would work like that, these stars could not exist. So they carry a lot of information about the material properties of these neutron stars. of course, what would be more beneficial or more helpful would be to have a simultaneous measure of a mass and radius, so that one could, for example, map this sequence. But it turns out that radius measurements are significantly more difficult, or at least complex. And that is clearly because it's very difficult to measure a size of an object of 10 kilometers, 400 light years away or more. Most of these radius measurements are relying on X-ray observations. And for example, a particularly popular method has been to look at X-ray bursters. So the point is that you have a accreting neutron star that is accreting matter from its companion, and eventually it has enough matter in its envelope, and it will undergo a thermonuclear explosion that will lift the envelope of the star. And at the moment when the lift happens, then the radiation pressure exactly cancels the gravity, and therefore therefore it carries information about the compactness of the star, and that is reflected in the flux of photons that come from there. These are extremely complicated measurements because they have many challenging astrophysical systematics to take care of. Modeling is needed. There has been a lot of progress in the past years, and here is, for example, one of the state-of-the-art measurements of such radio measurement. Now, this is roughly what such an X-ray burst looks like for a Rossi X-ray Timing Explorer mission. When it happens and then it cools down. And if you look at very high time resolution on the signal, you see that the signal has these wiggles, and these wiggles come with the same frequency as the rotational frequency of the star. And the interpretation is that there is a hot spot on the star, and as the star rotates around, the hot spot is either visible, or when it's towards you, invisible when it's behind the star, and that affects the X-ray emissions coming from that. Now, if we didn't have general relativity, this would be the end of the story. But because these neutron stars, they are almost black holes, light bends around them, and because light bends around them, we see at any given moment more than 2 pi of the whole solid angle, and you can see a little bit behind the star. Of course, the more compact the star, so the smaller radius or larger mass, the bigger the effect is. And here are some models that show how the signal, or this pulse profile, is affected by the bending of the light compared to the no GR version. So the more compact the star is, the bigger the effect. And so because of that, these pulse profiles are sensitive to the compactness of the radius and the mass. And currently there are a couple ongoing and planned missions that use this robust method to measure these radii. One is the NICER, the Neutron Star Interior Composition Explorer, that's on the International Space Station and has given its first results for one star, and there are a couple others that are planned, and these are very exciting prospects of new radius measurements in the future. Of course, the big new game in the town it comes from the gravitational wave measurements of neutron star mergers. We all have seen the signal where the two neutron stars in spiral and they collide somewhere here. We do not see the post-merger ring down, because that goes outside of the frequency band of the instrument, and associated with the gravitational wave signal, there is the electromagnetic counterpart, which was observed basically all possible wavelengths of light. And since the start of the running of the O3 of LIGO and Virgo, there has been many other events on tape. Now, from these gravitational wave measurements, we can learn a lot about the physics of the neutron star matter, and there are three most discussed ways of doing so currently. So I will discuss the tidal deformability during the in-spiral a little bit more later, but there are also other ways that you can use these events, especially if you have multi-messenger control of these events. The associated electromagnetic signal with the event can tell about the nature of the post-merger remnant, which is again whether or not you have a black hole or a hypermassive neutron star or a supermassive neutron star. That depends on the material properties of the stars and their compactness. And also in the future, it is possible that the post-merger signal, the ring down, would be seen in these events. And that would be extremely interesting because that carries information not of the equation of state only at very low temperatures, but the temperatures reached in the post-merger ring down can reach the range where the colliders operate, so they can be sensitive up to temperatures up to 50 MeV. So that is extremely interesting prospect in the future. But so let me just mention in more detail the tidal deformability constraint, because that is something that actively can help us understand the material properties. So during this in-spiral phase, when the two neutron stars are coming towards each other, these two neutron stars are sitting in each other's gravitational fields, and then thus they will experience tidal forces and tidal deformations. Now, how much a star or object deforms under these tidal fields is typically quantified by the tidal deformability, or lambda, which is just by definition the linear response coefficient that relates the quadrupole an external gravitational field to the quadrupole moment of the object itself. And so this is interesting because the more the object is deformed, the more this affects the gravitational wave signal. And for example, here is a simulation of two different stars with two different tidal deformabilities. Here, this lambda equals 0 is a point-like star that doesn't deform under tidal forces. Going here, compared to another object whose tidal deformability, this is a dimensionless quantity, is 400, but that is in the range where somehow reasonable models lie. And you can see that the tidal deformability affects the gravitational wave signal in an observable way. Now, this is of course very interesting because as I had in the previous slide, we LIGO and Virgo have seen the gravitational wave signal coming from this event, and thus they can put bounds on the tidal deformability. The tidal deformability was not observed in this event, so unfortunately we have only an upper limit on the tidal deformability, but also that is already very, very interesting. So this is the result of LIGO. There are, of course, caveats to these results. This is based on a linearized framework. There are 90% credence levels and so on. There's a prior on the spins of the stars, but of course these are all very carefully thought through and very reasonable assumptions. And with this, there's a result from LIGO and Virgo that the ability of these stars of 1.4 solar masses, which is the canonical binary star, should be less than 580. And this is very useful for them later in this talk. Okay, so let me now discuss what we know about the equation of state from theory. So of course we know that the equation of state is given by the Lagrangian of QCD. You just need to perform this one single integral and then you are done. But anyone who tried to perform this integral knows that it is a very difficult integral to perform. In the heavy ion context for small baryon number chemical potentials, we have this amazing situation that actually this integral can be performed numerically using lattice field theory, and non-perturbative information about the equation of state can be accessed. But unfortunately, this miracle does not extend to large chemical potentials, large baryonic densities, because of the famous or infamous sign problem, and one has to only resort to approximations. There's two approaches that one can go ab initio. One is low energy nuclear theories that are applicable at low densities, and at very, very high densities we can use methodology that particle physics has given us. Asymptotic freedom tells us that the strong coupling constant becomes small, and we can use perturbation theory at very high densities. Now, this is the equation of state now. So the pressure here as a function of Quark number chemical potential, and what's shown here is a calculation, a state-of-the-art calculation of a nuclear effective field theory that gives us reliable information about the equation of state at low densities. But of course, as you try to extrapolate these models or calculations to higher densities, you run into problems. And of course, these problems come roughly at the nuclear saturation density. And this calculation, this particular calculation here, extends up to 1.1 times the nuclear saturation density, where the authors quote systematic errors of plus minus 24%. Now the central densities in neutron stars are of course significantly higher, and so in order to have a full modeling of the star, one needs more information. Now we know that at asymptotically large densities, the coupling constant goes to 0. So it is a non-negotiable fact that at very high densities, the equation of state has to asymptote to this line given by the free quarks, and that's of course a powerful statement, but it is less powerful as it could be, because even though we know that it has to asymptote at some point, if we just know the asymptote, we don't know when and how. And so therefore, in order to somehow make this into a more useful constraint, we need to understand how this limit is approached and when is this limit relevant or reliable. And in order to do so,
may I just
go ahead.
I just want to say that free quarks, but we know that actually there is a color superconductivity in that case. It's favored over just free quarks. So it's more complicated picture than that, right?
That is true. At the Fermi surface, there is all kinds of things that happen. but from the thermodynamical point of view, the dominant component is still the whole Fermi C, which is this component that gives free quarks. It's true that in transport there is a lot of physics that will come into play. Now, okay, but in order to understand how you approach this asymptote here, what we need to do is we need to compute higher order corrections to this asymptotic result. Something that we have been doing with my collaborators for a longer time. So where we are now at is here. So in practical terms, what you need to do in order to compute the equation of state to high order in QCD is that you need to compute vacuum these bubble diagrams using the finite temperature field theory Feynman rules, and there's a prescription how to do so, a unique prescription. The next leading order correction arises from one single simple diagram, and when you go to next to leading order, you need to compute one loop order higher, and in addition to the higher order, in addition to these 3 loop diagrams, there's also a non-perturbative component that you need to do, and you need to sum over an infinite set of diagrams with infinite number of loops. This next to leading order, we know fully with quark masses that we have computed, and we have a full control of next to leading order at the whole T mu plane, so that we can interpolate between the zero chemical potential high temperature part to the zero temperature high chemical potential part. And currently we are working hard to compute the full next to leading order part at 0 temperature, where we have some partial leading logarithmic order results, and we are working on the full order. I won't talk to you today more about the details of these calculations, because this is a colloquium, but I would be very happy to give another talk somewhere else about it. But without further ado, once you perform these calculations, what you end up is a result like this. So you see that at very high densities, the perturbative result asymptotes indeed to the free quarks pressure. But as you go down to lower densities, the error bars go up. The error bars are estimated through a normal scale variation technique that is used in all high loop order calculations. And you can estimate what is the chemical potential or the density at which the errors become commensurate to those from the nuclear effective field theory calculations. And it turns out that at this order that we are, the densities where where we have the same plus minus 24% errors happens roughly about 40 times the nuclear saturation density. So of course, it would have been nice if we could use this result directly to neutron stars, but clearly we are using perturbative control at densities that are higher than those in nuclear in the centers of neutron stars. And in this diagram, the neutron stars sit somewhere, centers of maximally massive neutron stars sit somewhere around here. So what you see is that it's not quite where the perturbative calculations are reliable, but it's also very far from the region where the nuclear effective theories are reliable. And so what we will do here is to use the fact that we are close to the region where perturbative calculations become reliable, and we will use it, use the information from there to allow us to make better statements about the densities where the centers of the neutron star are. But we are not using these calculations directly at these densities. So the strategy here is that that we take these equation of states where we reliably know them, so at these low densities from nuclear effective theories and at high densities from perturbative QCD. And then we interpolate between these two limits. And what we do is we try not to add bias, and what we do is we try to find not only one interpolation between these two limits, but all reasonable interpolations that can be done. And by reasonable, I mean in a very flexible way. So we just demand that these equations of states are thermodynamically consistent. They match to these extremes. They are subluminal, so that they are causal, and they are smooth when they don't have phase transitions. Their derivatives can have kinks. And so then we try to find an interpolation, and then we try to find all possible interpolations that can be formed. And then we can use the astrophysical observations to weed out those equations of states that would not be consistent with the observations. And therefore, optimally utilize both the theoretical and the observational constraints that we have available. So, for example, how you would do that, you would take this density interval where we don't have a first principles control, and say split it in piecewise polytropes. There's nothing special about this particular functional form. It's just very popular among astrophysicists because this can describe many different types of matter. And so what you would do is you would take, here I plot the equation of state in a slightly different way, the pressure divided by the free pressure. And so what you would do is here you have the nuclear equation of state, then you have interpolating function that goes to some switching point, and then would change the polytropic index and do some until it reaches the perturbative QCD line. And so this would be, for example, this would be an example of a bitropic or a two-segment polytrope. And what you would do is you would take these two-segment polytropes and just vary all the parameters until you find the whole parameter region which is allowed by these theoretical boundary conditions. And so this is, for example, for these bitropes, this is the set of interpolating functions that you can form. Here it's plotted in this log plot where the errors look always much smaller. Of course, you might be worried that here there were only two segments and maybe nature is more complicated. So what you do is you add more segments and see that you have convergence of your results. And then you might be worried that perhaps this particular choice of taking polytropic equation basis function is not good, and maybe that adds bias. So then you try different basis functions, and at the end of the day, you see that you have convergence, and then you believe that the constraints that what you have come directly from the theoretical inputs and the observational inputs that you have put in, and that you have minimal amount of theoretical bias, and that's the strategy here. Okay, so now that we have the ensemble of equation of states, we can start weeding them out with using the astrophysical constraints that I mentioned earlier. So here is an ensemble of roughly 200,000 equation of states that are created from 4 segment polytropes, and there's no constraints on the parameter values. And now this is plotted again in a slightly different way. This is preferred by the neutron star physicists, the pressure as a function of energy density plot. Now you can take each and every of so this cloud represents 200,000 different equation of states. You can take each one of them and create the mass radius sequence of them, and that tells you what kind of stars are available with this ensemble. Now, because we know that there exists at least one 2 solar mass neutron star, if not 2, we know that any of these equations of states that I just created, any of these equations of states that does not support a 2 solar mass neutron star cannot be the one that exists in the nature. And that takes out equation of states that become soft too early. They would collapse into a black hole before reaching this mass. And by that, having this ensemble of equations of states and knowing that there's a 2 solar mass neutron star, we get a substantial constraint on the equation of state. This also allows to transfer the knowledge of the 2 solar mass neutron star into a prediction on the lower limit of the radii of the star at, say, 2.4 solar masses, which is 10 kilometers is here. Similarly, because we can take each and every of these equations of states and we can compute their tidal deformabilities, we can use that to exclude any equation of state that would lead to so large a radius that it would lead to so large tidal deformability that LIGO Virgo would have seen it in the gravitational wave event. And because of that, we can weed out a large amount of equation of states that would be too stiff. So the two solar mass neutron star cropped out equations of states that were too soft, and the tidal deformability constraint weeds out equations of states that are too stiff. So they nicely complement each other. And this, of course, gives us also a determination or a prediction of the radius of a 1.4 solar mass neutron star. This is actually the first determination of radius of a neutron star from gravitational wave measurements. And it has been repeated with different techniques by many groups, and the results are in good. They are in good match. Okay, so now we have this band of equations of states that we believe that is a determination of the equation of state. It would be, of course, nicer if the equation of if this band were thinner, right? And in some sense, we are victims of our own generality. The interpolation functions that we have, we allow for a very extreme equations of states. We allow for equations of states that have multiple phase transitions. We allow equations of states that have very rapid changes in their behavior as a function of density. And we also allow for equations of states that have extremely high speeds of sound. And here, for example, we show the equation of state now differential as a function of the maximal speed of sound that has been that is attained in the equation of state density. Now, there's no first principles reason why the speed of sound could be very high, but we still do not have almost any first principles microscopic relativistic calculations that would exceed, where the speed of sound would exceed the speed of sound of conformal matter, which is 1 over square root of 3. So you could say that there is certain theoretical bias for equations of states that extreme. Now, it may be that this bound is broken, but still you can ask how realistic are equations of state that have speed of sounds of, say, almost the speed of light. Now, this is an interesting question, and it contains some theoretical bias. And here I just show what happens to the equation of state if you assume slightly smaller speeds of sounds than speed of light. I also want to emphasize that the current best radius measurements are also, I didn't use them in the constraining of these equations of states, but they also are consistent with this hypothesis of not breaking the conformal bound by a large factor. I just leave that for you. Now, let me finally comment about the possibility of having quark matter in neutron stars. So let me pivot back to the heavy ion collisions for a second and ask, why are we confident that there is quark matter in heavy ion collisions? We know from lattice field theory studies, we know the equation of state in very high detail, and we know that there's no true phase transition. So there is no crisp definition of what quark matter is from that point of view. But what we see is that this equation of state can be understood at its limits at low temperatures and very high temperatures in terms of hadronic calculations and calculations based on QCD and partonic degrees of freedom. Here is a lattice determination of the pressure, which at low densities follows a hadronic model very well, and at high densities and high temperature follows the characteristic features of what we expect from perturbation theory, the quark matter to look like. The perturbative calculation might not be under theoretical control, but the characteristics of this equation of state are similar. For example, it is close to conformal, meaning that this is almost a straight line here. The normalization of the pressure reflects the number of degrees of freedom in number of quarks and gluons in the theory, and also the speed of sound is very close to the conformal bound and approaches it from below. And now, in heavy ion collisions, we can estimate what is the energy density that's attained in these collisions by measuring how much energy flows from a single event and having some kind of an understanding what is the volume of this collision system. And that gives us an energy density, what we expect that the system is. And this energy density is much higher than where we start to see this quark matter-like behavior. Now, in the heavy ion community, there's of course a lot of discussion about asking to what extent do we know that these particles are not just flying apart and really create a thermalized medium, and that is interesting discussion and has to do with heavy physics, and here that doesn't play much role. But the question that what I really want to ask is, how can we repeat this same logic now with neutron stars? And of course, with neutron stars, we don't have the lattice determination of the equation of state, so we are in a not as strong position to make these statements. But we do have this equation of state that we have constrained from observations and theoretical considerations. And I cannot help but to see that there seems to be a two phase structure here. So if I look at low densities, the equation of state looks very much like an extrapolation of the hadronic equations of states. And after some density, the equations of states look very much like an extrapolation of the perturbative results. Now, this didn't need to be so, but it is given to us by the observational constraints. And so that's why it is very interesting to ask, is this really reflecting a change in the active degrees of freedom in the matter as well? And so is it, and the way to interpret this is that here at low densities, you have hadronic matter, which then melts either with a strong first order transition or maybe a crossover into a quark matter. Now you could, by the way, this kink here happens roughly at the same energy density, and this was given by the observations, the constraints, happens roughly at the same energy densities as the phase transition in hot quark matter. Now, this is just a one observable, one characterization of the equation of state, and you might wonder if that is really enough. But what you can do is you can try to do better. So what you can do is you can try to characterize these different equations of states in this space that is spanned by these different characteristic features of these equations of states. So here what I have is a space that's spanned by the polytron x that the slope in the previous slide. Here we have the speed of sound at z-axis, and here we have the number of effective massless degrees of freedom, or the pressure divided by the free pressure. And we can now use this to characterize the different equations of states. Here I have this line here that corresponds to the prototypical quark matter. So what comes from a perturbative calculation, and this is where what we can say is a matter that lies here resembles perturbative quark matter. And at the same time, we have a bunch of lines here, which is the collection of all nuclear equations of states that we could find that were publicly available, don't contradict any observations. And you see that they also form a tight correlated bunch, which is very separate from the prototypical quark matter. So we have prototypical nuclear matter, and we have prototypical quark matter. Now, if we would assume, well, these lines correspond to equation of states, and so you can now ask, if we would assume that these nuclear equations of states were the reality, where would centers of different neutron stars lie? And so we can find out where the different centers of neutron stars lie, and here the bunch of points here correspond to the central densities of neutron stars built out of these nuclear models for neutron stars of mass 1.4 solar masses. And this bunch here shows where if the matter is nuclear matter at all densities probed, the matter is nuclear matter all the way into the center. This would be where the central densities lie. Now we have our ensemble of equations of states, which is the empirical determination of the equation of state. These equations of states, of course, start first following the nuclear equation of state, eventually reach the PQCD by construction. So they will start from here, and they will reach the perturbative QCD, because we know that these were the inputs that we put in our calculation. And now what you can see is, so this is a representative set of these 200,000 equations of states that we have. And now what we can ask is to what extent the centers of the neutron stars on these interpolated equations of states resemble those that come from purely nuclear equations of states, and to what extent they resemble those that would come from our prototypical quark matter equation of state. And so these are now the densities that are reached in different stars in these interpolated equations of states. So you see that here, these are the 1.4 solar mass neutron stars. And there you can see that there's a significant overlap between the nuclear models and the interpolated equations of states. So the statement that I would make is that at least it seems that for 1.4 solar mass neutron stars, the interpolations are consistent with the nuclear models, and therefore we would say that the matter is nuclear all the way to the center. The situation is very different when I look at maximally massive neutron stars. So here were the nuclear equations of states for maximally massive neutron stars. And this is where the interpolations lie. And you can see that now the centers of the stars of these maximally massive neutron stars end up in a region where the equations of states resemble much more the prototypical quark matter equations of states. By the way, if you want to see a nice 3D video, you can go to this link, and there's another link which gives you a video form of this three-dimensional space. But so the main conclusion from here is that it doesn't seem that there is quark matter in the cores of 1.4 solar mass neutron stars, but it seems that there would be quark matter for most of these equations of states in maximally massive neutron stars. Now you could ask how much of the star is in this phase that resembles more quark matter, and you can set up some kind of a rough definition of what you mean by the quark matter here, just to get the feel if there's 1 femtometer cube of this matter, or if the sizable part of this is made out of this matter that resembles quark matter. We used was just use the slope of d log epsilon to have a quantitative feel of how large these quark cores should be. And it seems that if the speed of sound is not extremely high, then these parts of the stars that are in the quark phase are very large, and they can carry significant amount of total mass of the stars. And it seems there are cases where there is no quark matter if you allow the speed of sound to reach close to 1, and at the same time have a large first order phase transition. But even if you don't have quark matter in the maximally massive neutron stars, it is interesting that the collapse of the star to a black hole is triggered by the phase transition to quark matter. Okay, so that's where we are now, and the future is very interesting. So at the same time, there will be there's a push from the nuclear physics community to improve calculations to get to higher densities with good confidence, and at the same time we are working hard to bring down these PQCD calculations to smaller energy densities, so that we can push these uncertainties from the both sides. And at the same time, there will be many observations coming from gravitational waves and radius measurements that will certainly allow to weed out more of these equations of states and allow us to have a better understanding of the equation of state where we cannot do first principles calculations. So that is, and that will certainly lead into stronger statements in the future. So let me now conclude. The competition between gravity and pressure of strong interactions make neutron stars unique femtoscopes. There's a very rapid advancement in astronomical observations, both from the gravitational wave observations and traditional radius measurements. We are working hard to improve our calculations to next to leading order and making progress there. And the combination of these observational and theoretical inputs gives us a handle to determine properties of strongly interacting matter in the conditions where we don't have first principles calculations. We may have seen some hints point that there might be quark matter in maximally massive stars. We cannot, of course, give definite answers yet, but at the same time, it seems, at least to us, that quark cores are not the exotic alternative, but they should be treated as the standard scenario. And finally, I want to connect this to a broader community, which comes from the fact that by doing this kind of a not model independent analysis, we can also see it breaking. It's possible. So far, all the different constraints that we have put or studied, they have been in good agreement with each other. They've been complementary or consistent. It is possible that this consistency will break. It might be that the radius measurements and the tidal deformability measurements, for example, will be inconsistent, and that would be a sign that the assumptions that we have made are false. And the assumptions that we base these studies is QCD and general relativity. So seeing inconsistencies in this framework would be an indirect way to see that there might be some beyond QCD and GR physics going on in these stars. So thank you.
Okay, thank you very much for a nice presentation. We have a number of questions, so I'll give the first question to Vivian. Vivian and Sarah, please.
Thank you. Thank you. Thank you for an excellent presentation and a very, very interesting result, very exciting results. I just want to be sure first that I understood the scope of your results. So at some point you said that your equation of a state, I mean, the way you did your calculations allowed for different change, different phase transitions, etc. So it seems very general. So that's the first thing I want to be sure I understood correctly. And if that is the case, my comment is, have you thought, or maybe it's time to start to put constraints coming from transport properties, because that would be very important to not only to define or decide if quark matter is actually inside the core, but also what phases of quark matter are more suitable for the observation. So have you thought about that, or do you have any comment to make on that?
Well, first of all, so we indeed have used extremely versatile set of interpolation functions. We've used these 4-segment polytropes. We've used other bases based on interpolation of piecewise interpolation of speed of sound. We've looked at spectral methods having Chebyshev polynomial forms of the spectral index and so on. So we really have tried to cover all these bases, and we see convergence of our results. So I think we've tried to do as thorough job that way. For transport, that is absolutely a very interesting question, and I would certainly want to use constraints from the transport. However, right now at this point, I do not know of any explicit constraint that I could add to our framework. But indeed, that would be, it's not just enough to know if you have quark matter or not. You really would like to know what its phase is.
Exactly.
And so indeed, it is a very interesting question.
Okay. Second question comes to Pavel Danilevich.
So I wanted to comment on the lower end of the energy densities that where you speculated about the possible transition. So these kind of densities, so the 500 MeV per cubic Fermi, that's under 3 times normal density. And this kind of densities are routinely run over in collisions, heavy ion collisions in GeV range. And there's nothing there jumping. There's no transitional behavior. There's no phase transition evidence. If you were to talk about 700, then it would be tougher. I don't think you can make a strong claim from collisions because the matter begins to be dominated by pions. If you want to increase the density, you have to increase temperature and you produce pions and resonances. And it gets tougher, particularly if you want to extrapolate to cold matter. such as in neutron stars. So anyway, the lower end, I think, can be excluded on the basis of heavy-ion collisions as far as transition is concerned.
That's right. And that is an extremely interesting question on how to combine, have a unified description of both low energy heavy ion collisions and or mid energy, I should say, collisions and these neutron star collisions, but that
ultrarelativistic collisions.
To make a strong model independent claim, one needs to extend this formalism, for example, to add temperature effects to this, and this is something that we are certainly working on, and that is absolutely very interesting direction.
Thanks.
Okay, next question is Jorge Karevich.
Yeah, so thank you again for a nice talk. So what I would like is if you can clarify a little bit better your statement about nucleonic equation of states being inconsistent. So for example, there are equations of state that describe, of course, the properties of finite nuclei around normal nuclear density and are still consistent with all the observational constraints coming from LIGO, from NICER. So what exactly is, when you had, I think it was next to your last, yeah, so there. So what exactly is the meaning of hadronic models are inconsistent with maximum masses?
So what is inconsistent here is the interpolations and the hadronic models. They do not overlap. So here what we have said is that these interpolations represent an empirical determination of the equation of state, so that the true equation of state has to be among these interpolations. And what we see is that the hadronic models don't overlap with these interpolations. Therefore, we say that these interpolations are not in a hadronic phase.
If Igor, if you give me just a chance, but what should I do with an equation of state with exclusive nucleonic degrees of freedom that actually satisfies all the constraints that you mentioned? So why is that inconsistent or excluded? I mean, I want to understand exactly what it means by inconsistent. If I have an equation of state with no other degrees of freedom than nucleonic that satisfies all astrophysical constraints.
But it should also satisfy the constraint that at high density, it reaches perturbative QCD.
But we don't push them to 40 times nuclear matter density, right? I mean, we need to push them probably 8 times nuclear matter density to get the heaviest neutron star. So 40, it seems to me, it's, anyways, maybe that's enough. And I appreciate your response.
Can I make a comment here, Igor? Is Veronica?
Okay, go ahead.
I think the issue is that although there are many parameterizations for nucleonic equations of state that can fulfill astrophysical constraints, we have to be careful, because if you do not allow a phase transition to quark matter, the hyperons must be included. So there's nothing preventing the hyperons, if you allow them to appear, not to be present at a few times saturation density. So, and then when you include the hyperons, it becomes much more complicated to fulfill all the astrophysical constraints.
So what I would say is that a nuclear equation of state that reaches 2 solar mass neutron star and is consistent with astrophysical observations, that is the set of black lines here. These are self-consistent equations of state. Just by looking at these equations of states, with the observations, you cannot determine that they would be excluded. However, we know that any of these equations of states must reach at densities that are not probed in neutron stars. They must reach the asymptotic expression coming from PQCD. And if they are not consistent with that, then they cannot be consistent with nature. That's the logic.
Okay, Efrain, go ahead.
Yes, first, thanks for the interesting talk. My question is more to ask you for a comment about how well is known nowadays the dependence on the strong coupling with the density, because that will be a very important point, I think, for the extrapolation, no? To know what will be already the real density, where you can already claim that you have a perturbative QCD regime.
So you're asking about running of alpha S as a function of chemical
How
potential.
well, yeah, how well is nowadays known? Because I know that that was a big question years ago.
The more relevant question to ask is how does the equation of state vary when you vary the renormalization scale? That quantifies the uncertainty that comes from running of alpha S. And so there is, of course, you know that the final result does not depend on the renormalization scale. But if you truncate the equation to some order in alpha S, then the results will depend on that. And so what the error bars that I showed you came from such a variation of the renormalization scale. And they quantify these higher order, the relevance of these higher order terms. I should also mention that there is the perturbative expansion is an asymptotic expansion and doesn't have a finite radius of convergence. And so one uses in these calculations a criterion of apparent convergence, where you demand that when you compute higher orders, the scale variation errors at higher orders are within the scale variation errors of lower orders, which also risks the usage of these results in the form they are at very low densities.
Okay, thank you.
Okay, next question is Thomas Schaefer.
Hi, it's Thomas. Nice talk, Aleksi. Correct me if I'm wrong, but so if I understand correctly, the constraint that you impose is the following. You take your calculation of the perturbative equations of state. I can actually also start my video. You take your calculation of the perturbative equations of state, and you demand that the accuracy of these calculations is this plus minus 25%. And then you say, in this regime where they become accurate, they must also be true. So you demand that any equation of state that's physically reasonable must extrapolate to PQCD in a regime where the internal accuracy of PQCD is plus or minus 20%. But that's of course not really a logical argument. It's not the case that just because the calculation is internally consistent, it must also be true. I mean, if I'm a pessimist, I tend to be an optimist. I agree with you, but I think as a logical argument, it's not watertight, because it doesn't have to be that way. Just because the calculation is internally consistent, it's also true.
That is a true statement, what you say. However, I think we have plenty of reasons to believe that asymptotic freedom and QCD are at play.
But aren't you sort of assuming tacitly that there is some sort of continuity, more or less? If there were a huge jump and a very sudden first order phase transition at some point, that sort of beyond the observable region of the densities in the stars, but still far below the asymptotic freedom, there could be some sudden, very sudden change, and you would miss it this way.
So these we account for by having these very versatile interpolation functions. And indeed, those cases where we don't reach the quark matter phase, they are exactly equations of states like that. They have first a very stiff equation of state that's almost has a speed of sound of 1, and then you have an enormous phase transition that ends again to a very extreme case that then finally reaches the
well,
perturbative.
Technically true, but for example, you were using the constraints from the lambdas being bounded by a certain value. If the lambda changes dramatically with the density, it could be less than 550 below certain density, and that's the observable constraint you see. But at larger densities, for example, it could be so much larger that you simply artificially impose that constraint, which is not valid.
That is correct. So as you see here, line is the 1.4 solar mass. Solar mass of 1.4 solar masses. And because what we use here from LIGO is this linearized framework where they give the result of the tidal deformability for a 1.4 solar mass neutron star. You can see that that's where the constraint is the most stringent. You see that below that value there can be a versatile behavior, these interpolation functions, just because we didn't constrain that particular value of tidal deformability. Now, that one could improve on that, and if the stars that collided in this gravitational wave event exactly at 1.4 solar masses is used as an expansion point in this analysis when you give the result in terms of 1.4 solar mass star, then where this feature would appear in this constraint would of course shift with, and so there is some possibility that you can wiggle around that point.
Okay, there is another question still. Adam Bauer.
Hi, thanks for the really interesting talk. I was just wondering, when you were kind of arguing that there was a phase transition when you extrapolate from the very high energy density and you get to extrapolate from the very low energy density, that there is a phase transition. Are you saying that if there is a kink in the equation of state, that would indicate there's a phase transition? Is that kind of the argument that you'd make there?
Yes, that is correct. But by phase transition, I mean change in the characteristic degrees of freedom, not necessarily a discontinuous phase transition. It could be discontinuous phase transition, but it also could be a crossover in the way it is, for example, at zero chemical potential at high temperatures.
Thanks.
Okay, I don't see any other questions from the audience. So I think we had enough discussions then, and indeed it was a very nice talk, creating a lot of discussions, and that's the best type of talks. So thank you very much for your time to prepare the talk, and thank you very much for an interesting presentation. And I think with that, we will be finishing, unless somebody jumps with a question at the last moment.